In the vast expanse of space, located at a staggering distance of 7 billion kilometers from Earth, an unexpected finding has emerged, one that has sparked great interest among scientists and space enthusiasts alike. This remarkable observation, originating from Proxima Centauri b, the closest known exoplanet to our own, has rekindled the age-old question of whether we are truly alone in the universe. The James Webb Space Telescope, JWST, with its powerful and sensitive instruments, focused its gaze on this distant world and revealed something utterly astounding: unusual bright lights emanating from the planet's surface. The phenomenon is unprecedented and has raised numerous questions. What could be the cause of these unusual lights on Proxima Centauri b? Could they, in any way, indicate the existence of life beyond our own planet? Could this be the moment when humanity comes face to face with proof that intelligent civilizations exist in the cosmos? For many years, decades, even, mankind has longed for and actively searched for signs of life beyond our solar system. From listening for radio signals to sending interstellar messages and scanning the night sky for habitable worlds, any hint, any anomaly suggesting the possibility of extraterrestrial life has always been met with overwhelming excitement and enthusiasm. Recently, this collective yearning has found new fuel. The scientific community was collectively stunned when the James Webb Space Telescope captured what many are now describing as compelling, even groundbreaking, evidence pointing toward the existence of life forms in space. As the telescope continued its mission, exploring the deep recesses of the cosmos and transmitting critical data back to Earth, it recorded what can only be described as unique urban lights coming from the exoplanet Proxima Centauri b. These lights, as their very name implies, resemble artificial illumination. They appear to glow in structured patterns, not unlike the lights of a distant city as seen from space. This has led to one of the most intriguing hypotheses in modern astrophysics, that an alien civilization may indeed exist in this nearby star system. The notion is both captivating and perplexing. It has filled scientists with wonder, curiosity, and a cautious sense of hope. Each researcher, each institution, is currently grappling with the staggering possibility that this could be the discovery they have all been waiting for. If these lights are, in fact, artificial in nature and not the result of some yet unknown natural phenomenon, it would mean that intelligent life forms capable of developing structured societies and generating artificial light exist beyond Earth, and we are just now beginning to detect them. Observing these urban lights from a mind-bending distance of 7 billion kilometers, NASA engineers have found themselves asking one pressing question: how long have these lights been glowing in the cosmic night, patiently awaiting the moment when mankind would develop the technology needed to detect them? David Kipping, an astronomer at Columbia University, has taken particular interest in the findings. He characterizes the exoplanet Proxima Centauri b, where the urban lights have been sighted, as a celestial body with peculiar heating patterns. These thermal anomalies differ significantly from those typically observed on other known rocky planets. Whereas conventional rocky planets absorb sunlight and then emit it as infrared radiation, Proxima Centauri b appears to possess a markedly different infrared nature when compared to its host star, Proxima Centauri. This peculiarity has, in fact, made it an excellent candidate for detailed observation by the James Webb Space Telescope. The JWST, renowned for its unmatched sensitivity to infrared wavelengths, is uniquely positioned to capture even the faintest glimmers of light radiating from faraway worlds. Because of this, the thermal signature of Proxima Centauri b has become a focal point in the investigation of universal secrets, specifically, those concerning planetary atmospheres and their ability to sustain life. By taking full advantage of JWST's state-of-the-art infrared imaging capabilities, scientists are embarking on a comprehensive mission to unravel the mysteries hidden in the planet's atmosphere. They aim not only to understand its chemical composition but also to evaluate its potential habitability and, perhaps, the likelihood that it harbors life. What makes the JWST so effective in this pursuit is its extraordinary infrared sensitivity. This capability allows it to probe the night side of Proxima Centauri b, an otherwise daunting task, because it can detect even the faintest of light signals that might be lost in the cosmic darkness. As such, the JWST becomes an ideal instrument for verifying the presence of possible sitter-like lights on the planet's night side. Its precision lies in its ability to operate within an extremely narrow frequency band, one that is 1,000 times narrower than the frequency of starlight. This specificity provides scientists with a powerful tool to distinguish artificial light sources from natural celestial emissions. Adding to the intrigue is Proxima Centauri b's interesting relationship between its stellar features and surface conditions. Its day side, bathed in light from the red dwarf star Proxima Centauri, appears to be adorned with structures that resemble solar panels, presumably harvesting energy from the host star. Meanwhile, Its night side endures much colder temperatures, creating a dramatic thermal contrast across the planet's surface. These variations are determined in part by the composition of the planet's atmosphere, an element that astronomers are especially eager to understand. The JWST has the ability to effectively analyze the planet's thermal emissions, thereby providing critical data on atmospheric pressure, molecular content, and potential greenhouse effects. Adding another layer of opportunity is the JWST's orbital positioning. Its orbit around Earth aligns in such a way that it enables full observation of Proxima Centauri B's diurnal and nocturnal cycles, which are completed in just 11.2 Earth days. This alignment allows for thorough, uninterrupted monitoring. The next logical step in this groundbreaking mission is to assess the planet's atmospheric chemistry to determine its potential to support life. Scientists are particularly focused on identifying the presence of gases such as oxygen, water vapor, and methane, all of which are considered key biomarkers of habitability. If these elements, oxygen, water vapor, and methane, are indeed detected in the planet's atmosphere, it could signify that Proxima Centauri b is capable of supporting life, at least in conditions familiar to us. However, this is no simple task. The process involves the meticulous capture and analysis of light rays passing through the exoplanet's atmosphere during transit events. Though the James Webb Space Telescope possesses exceptional capabilities for characterizing planetary atmospheres, it does have its limitations. Specifically, its focus is primarily geared toward analyzing variations in the concentration of more readily detectable molecules such as water vapor, carbon dioxide, and methane. Detecting oxygen, a crucial component of life as we know it, is far more challenging, and the JWST's ability in that regard is somewhat limited. Despite these constraints, the telescope compensates by seeking out other markers, such as ozone, which may also provide vital clues about a planet's habitability. It is also important to acknowledge that the JWST cannot explore all potentially habitable worlds. Its range and observational reach are restricted to the nearest exoplanets to Earth. As a result, astronomers are turning their attention toward ground-based observatories for deeper insight. One of the most anticipated instruments in this regard is the Extremely Large Telescope, ELT, which is expected to become operational in 2028. Once functional, the ELT will allow for more comprehensive and in-depth investigation into the atmospheric structure and composition of distant exoplanets. Scientists across the globe eagerly anticipate the development and deployment of future space telescopes that will take exoplanetary exploration to new heights. While the JWST remains an indispensable tool in the current era, its successors will likely push the boundaries of our understanding even further. One primary goal for future instruments is to reduce the glare from host stars, thereby allowing more accurate studies of light reflections from exoplanets themselves. This represents a significant technical challenge, as researchers will need to distinguish between gases that are biologically produced and those that result from geological or chemical processes native to the planets. Nevertheless, the scientific community remains